Right. Okay. So let us start. So today actually we will be dealing with the coupled circuits, and this is a simple and small concept, but this is an important concept also. Right. Coupled circuits. So what is this coupled circuit? Is actually this comes in the context of the mutual inductance. So this is coupled circuit in relation to mutual inductance. Now let us see what is this inductance, right? So inductance actually it comes from three different principles. So one is actually the first principle is the Ampere's law, which states that whenever there is a flow of current, there induces a magnetic field. Suppose if there is a coil like this, it may not be a coil, it can even be a straight conductor also. Whenever there is a flow of current I, then actually around this conductor actually it induces a magnetic field. Now, suppose if this is a straight conductor, if there is a current that is flowing in this direction, then actually around this actually there is a magnetic field actually that is going to be induced. And this is the Ampere's law. And the second law, that is, whenever there is a flux linkages of the magnetic flux linkages with the conductor, then there induces an EMF. So this is the Faraday's laws of electromagnetic induction. What it says is, suppose this is a fixed current like DC current, actually there won't be any change. So there is a magnetic field that is going to be induced and it stays as it is. And because of that reason, so there is no inductance actually we consider in the case of the DC voltage or the DC current. But in case of AC, what happens is, so this is, if there is an alternating current that was given, then actually there is a continuously changing magnetic field is going to be produced in this particular conductor. Now suppose it will assume that this is actually a sinusoidal current, let us say, then actually it is going to produce the magnetic field which is increasing in nature, and then actually it will reduce to zero and again actually goes in the opposite direction. That is the direction actually it will become opposite. So there is in the positive half cycle actually if it is keep on expanding in one particular anti-clockwise direction, let us say, and in the negative half cycle actually it will try to converge into the opposite direction, the magnetic field, and the strength of the magnetic field is continuously reducing and increasing. So it is going in the positive direction, a higher value comes to zero, goes in the opposite direction, again comes to zero and goes in the positive direction. This way there is a continuously changing magnetic field is going to be produced because of the alternating voltage if it is applied to any particular wire. Now here in case actually the direction of the magnetic field we can find with the help of the right hand thumb rule, which says that if you hold the thumb like this, then actually let us say this tip actually pointing towards, so this thumb actually pointing towards the current direction, then all the four fingers actually, which is like a circular fashion, which will give the direction of the magnetic field that is going to be induced, right? And this is actually the Ampere's law. And Faraday's laws of electromagnetic induction, what it says is, this changing magnetic field, if it is intersecting with the conductor, that by default happens in case of any alternating voltage. Suppose actually if the magnetic field is continually increasing and decreasing and going in the opposite direction, it will cut the conductor, right? The same thing happens even in this coil also. In this case of coil, actually we are trying to increase the magnetic field strength by putting like a coil. So the length of the conductor is increased within a smaller duration. So that's why actually you are putting a coil like this. Then actually if you apply the right hand thumb rule again, you can hold the conductor like this so that actually you can identify the magnetic flux direction. And this magnetic flux actually it goes in this particular way internally, and externally actually it will come back and then actually it will go like this. So this is the top direction, right? And this way actually the magnetic field actually is going to be induced in this particular inductor. And this magnetic field actually it will not stay as it is. So it is actually continuously increasing and decreasing. And then actually the strength actually it will try to increase and decrease like this, and then it will try to intersect it. And this process is called as the flux linkages. Right? So these are called as the flux linkages. So that is, this is called, there is a term called the flux. So flux means actually, this is a general concept. It is not like actually, I will give you the simple example of the flux because this is very, very big subject to discuss. And in the EMTL, actually, we will discuss this flux concept to a greater extent with the help of the vector calculus. What exactly means by the flux is actually, I will give you a simple example. which you can easily understand. So there is a concept of force actually in physics, right? Now, if you notice, suppose actually if there is a block of mass like this, and this actually if you apply a force here, now in this case actually the force by default it will have three different characteristics. One is actually the magnitude of the force. So one is the magnitude, and the second one is the direction of the force, and the third one is point of application of the force. Right, so these are the three important characteristics that are associated by any force. Right, just a minute. Right, okay. So this is actually, so these three important characteristics actually any force is having it: magnitude, direction, and the point of application of the force. Now I will give you another example. Suppose if I drop this particular pen, because of the gravitational force, it is going to be going down. Now here actually it is having a magnitude called as the weight, and it is having the direction towards the ground always. And there is one more actually the point of application of the force actually that we cannot find out here, because suppose if I go to Bangalore and then actually if I drop the pen, again actually it is going down only. And if I go to Agra and then place this down, then actually it is again going down only. But where is the point of application of this force? Can anybody comment on this? Where exactly is the point of application of the force? Guess where it is? Anybody can comment it. What is the point of application of this particular force? So the gravitational force actually what we are feeling now, which is distributed everywhere. It's not at a single location, everywhere actually it is placed. And because of that reason, this kind of force where it is having the influence at everywhere is called as a flux. So flux means actually we cannot exactly pinpoint where exactly it is there. It may be having different magnitude, it may be having different direction, but it may be having a different point of application. All such kind of field together we call as a field, right? Now this kind of thing actually happens at multiple places. So the gravitational field you can think of, the magnetic field you can think of, and the electrostatic field actually you can think of. Even the fluid field also actually you can think of. Suppose if the water is flowing, then what exactly is flowing? So every particle is having a different magnitude of the velocity, a different magnitude, it's a different direction of the velocity at every point. So how to quantify the entire water? Because if you make it to partition, you can make infinite particles, and every particle is having a different direction. So such kind of analysis, if you wanted to do it, the concept of the field theory comes into picture, right? So the field actually we will be distributing in this particular format. So this is, so phi of some x comma y comma z into I plus psi of x comma y comma z into j plus xi of x comma y comma z into k. Right, so this is actually the magnetic field, or actually the fluid field, or the electrostatic field. It doesn't matter whatever may be the field. Okay, right? So everywhere actually the concept of field comes into picture, right? So field actually usually expressed like a vector. Now this is actually this particular mathematical expression, which is a vector expression, and phi psi xi value is dependent on the position. So x, y, z values actually it decides the magnitude of each variable in this, and overall I, j, k values actually will decide the direction of it. And the point of application of the force is actually everywhere. So you can have any random values of x comma y comma z where it shows the point of application. So all the three characteristics are associated in this particular fixed vector. So this vector actually is called as a field vector or a flux vector we can think of. So this is called as the flux. Now in the case of suppose magnetic field, if you take it, so this magnetic field actually it is having the influence everywhere. So here actually I have drawn only two circles. That doesn't mean that actually it is not having the influence at this particular point. That doesn't mean that it is not having the influence at this particular point. Everywhere it is there. Just to have a glimpse of its direction, actually we have shown this one. Every corner, every micrometer actually you can find the influence of it, right? And this kind of nature actually is called as the flux. Now this is actually distributed everywhere. All these lines actually we call together as a flux, and here in this particular case this is called as a magnetic flux because this is a magnetic field. So this is a magnetic flux, right? So this is a magnetic flux, and this is all. So synonym is actually the field, magnetic field. Now this flux actually linkages, meaning if these flux lines are intersecting with any of the conductor, then that is called as the process of intersecting the flux linkages with the conductor is called as the flux linkages. So the process of intersecting the flux lines with the conductor is called flux linkages, right? So this is called as the flux linkages. Now whenever there is a change in flux linkages, obviously that happens in case of any alternating current. If it is flowing with any of the conductor or any of the coil, then actually the flux actually continuously it is changing. Obviously actually it will cause the change in the flux linkages magnitude, right? So this flux linkages actually is called as N into phi, where N is the number of turns of the coil intersecting with a flux. With a flux magnitude of phi, right? So N into phi actually is the total flux linkages. So the phi is the flux by magnitude because we need to quantify somehow. So this is actually, it is measured in Webers, right? So it is measured in the Webers. So Weber is a scientist name who invented this. So that's why actually it was given the name Weber, capital W, small v, right? Webers. And N phi is actually the total flux. Now the rate of change of flux linkages. So N into d phi by dt is the EMF that is going to be induced. So N into d phi by dt is called as the EMF that is going to be induced, right? So the rate of change of flux linkages always causes EMF. This is the Faraday's law, right? So the rate of change of flux linkages induces an EMF. It induces an EMF, right? And so as per the Faraday's law, right? And so it's not stopped at that particular point. Now the direction of the EMF also we need to be identifying. So the direction of the EMF, that is, suppose if there is a current that is flowing in this. So let us take this particular scenario. So try to understand all this concept very so carefully. Actually, you try to understand this concept because actually this single concept actually it drives the entire electrical engineering. So not only the circuit theory, so it will be very rigorously used actually in the case of the electrical machines, right? Where this is completely dependent on this coil, right? And now actually, if there is a current that is driven by this particular voltage V, which is Vm sine omega t, and this current actually it flows like this, and obviously this is a changing current, and this changing current actually will induce a changing flux, and this changing flux actually will cause the intersection with the same conductor, hence actually it is going to produce the EMF, and that EMF will be in such a way that it will oppose the cause of its creation. So the EMF induced in the coil is in such a way that it opposes cause of its creation. Right? Now here, what is the cause of its creation? So the flux linkages that are causing the EMF to be induced, right? And that flux linkages actually it wanted to reduce it. So to reduce that, the flux, so N is anyway constant, and phi value actually it wanted to reduce, obviously, because actually N actually it can't change because the number of turns are anyway fixed for a coil. And that flux value, if it has to be reduced, then the flux actually, why it was induced? Because of the current that is flowing. And that current actually is driven in this particular direction, and this directional current by magnitude whatever it is flowing, it will produce a flux proportional to this particular current. That means phi is actually proportional to the current that is going to be flowing, right? And how much it is going to be there? So this is actually n phi by Ia. So or actually, so this value actually it is proportional. The amount of the current that is flowing actually will proportionally induce the magnetic flux. If the current is reduced, the flux is going to be reduced. If the current is increased, then actually the flux is going to be increased. Now actually it wanted to reduce the flux. So to reduce that particular flux, what it will do is it will try to induce an EMF in this particular coil, so that actually in opposite direction, if it drives the current, then actually the amount of the effective current is going to be reduced, and hence the flux is going to be reduced. So that means actually it will induce an EMF this way, so that actually if this is positive, this will also positive. If this is negative, this is also negative. In that way, actually it will try to induce an opposite current. According to that, the EMF is going to be induced. Got it? I hope you understood this concept. And this is called as the Lenge's law, right? So this is called as Lenge's law. So this is called as the Lenge's law. It opposes the cause of its creation. So the EMF is in such a way that it always wanted to reduce the current which is causing its flux to be created. So this is the value. And this value actually, by definition, actually we usually use LdI by dt, right? And this is actually the where L is called as the inductance, right? So and so this is actually L is given as n phi by I, right? So basically actually what we do is this is a proportional, and the flux linkage is actually you can say that actually n into phi is proportional to I, obviously. So the number of turns actually, so more number of flux intersecting with the conductors, hence actually n into phi is the effective one, and this proportional actually we will replace with a constant. So this is n phi is equal to L into I, or L can be treated as n phi by I. So this can otherwise be stated as the flux linkages per unit current is defined as the inductance. So the flux linkages per unit current is called as inductance. This is called as the inductance. L is equal to n phi by I. Now this is actually basically coming from the fact that there is a flux that is going to be produced, and that flux actually intersecting with the coil itself, the same coil. Then actually because of that the flux linkages actually it is happening, hence it is going to produce an EMF. Now the condition is that is it the current that is producing the flux because of the same coil, is it the only cause to induce this EMF, or else actually if I keep one more coil here and then actually it is no way connecting here, but actually there is a current that is driven in this particular case, then actually even the flux produced here, will it have an influence on the first coil? That is the question. Will it have it, or actually it will always wanted to induce the EMF because of its original creation, or actually because of the other coil also will have the effect? It will have an impact, right? So because everything is actually the magnetic flux. What Faraday's law says is it won't specifically say that the magnetic field induced by the same coil. So any magnetic field, as long as actually it is intersecting with the current, as long as it is intersecting with the conductor, then it induces an EMF. Now that magnetic field from the different field also, you can even keep a magnet over there. So even then also actually you can find the magnetic field actually, which is intersecting with the conductor, and it causes the current to be flown, right? Now this is, suppose if there is another coil, which is close by, if it induces a magnetic field, it will have an impact on the first coil, right? Then actually we need to quantify that. So to quantify that, what we will do is, so the one case is actually the flux linkages due to the flux produced by the same coil. Right? So the flux linkages due to the flux produced by the same coil causes an EMF and the corresponding inductance is called as the self-inductance. So this is called as the self-inductance. So that means, let us say there is a current over here, I, and the flux produced is phi, and this is going to be of N. Then actually the L value is called as N into phi by I. So this is called as the self-inductance. So it is the single coil and the single flux and the single current. But in case if we have two different, so let us say there is one coil over here and there is one more coil over here, though electrically not connected at all, but still if there is a current that is going to be flowing here, let us say this is of I1 and this current actually is going to be of I2, and this produces a flux of phi1 and this produces a flux of phi2, then in this particular context the L1 is the self-inductance, which is going to be N1 phi1 divided by I1, and L2 is the self-inductance, so N2 phi2 by I2, right? And there is a concept of mutual inductance. The mutual inductance is the flux produced by phi1 and the flux produced by I1, it will intersect with the second coil also, which is having the number of turns as N2, and this is of N1, right? So the flux produced by phi1, which is intersecting with the second coil, and this is actually phi12. So produced by 1 intersecting with 2. So this is actually phi12. And the counter the other way, the flux produced by phi2, it is intersecting with 1. Then actually this is what we call as the phi21. So phi12 and phi21. Then actually, so the total, so there is a fraction of the flux produced by the coil N1 will intersect with second coil, right? And this we need to quantify how much, that question actually we need to be answering. So to answer that particular question, there is a concept of coefficient of coupling. Right? Coefficient of coupling, which says that this is actually usually represented with a letter called K, and this K value is 512 by 51. So that means produced by 51, so produced by the first coil, and out of the total flux of 51, there is a component of 512 is intersecting with the second coil. And this value, even the second coil actually what it is going to be producing by 52. Usually these two are actually one and the same. So how much fraction it is contributing to the other one, the same fraction actually it is going to be contributing to the first one as well. So this ratio is called as the coefficient of coupling, right? And so then actually, so you can express 512 is equal to K times of 51, 521 is equal to K times of 52. So this way actually you can quantify this. So if you take the K value as the coefficient of coupling, then actually this value is 512 is K times of 51, 521 is equal to K times of 52. And then actually the mutual inductance is defined as coil 1 on coil 2, right? Mutual inductance of coil 1 on coil 2. Now, so here actually this is defined as a letter M, mutual inductance. So the flux produced by the first coil which is intersecting with the second coil, and the second coil will be having the N2 turns, and out of that actually 512 is the amount of the flux actually that is going to be induced. So N2 times of 512, and this was produced because of I1, and this is what we call as the mutual inductance of the first coil on the second. Got it? I hope you understood this. So N2 is the only difference. 512 is the flux produced by the first one, a fraction of it actually which is intersecting with the second one per unit current of I1 is defined as the mutual inductance of the first coil on the second coil. Exactly in the similar manner, the mutual inductance, so this actually if you call as M12, then this you can call as M21, and this is N1 521 divided by I2, right? So this is how actually you can define the mutual inductance of the second coil on the first coil. Now for all practical purpose actually this value is one and the same. M12 is equal to M21, and this is usually treated as a single letter called M. Then actually if you calculate, so M square if you calculate it, and the multiplication of this is N1, N2, 512, 521 divided by I1 into I2. So this way actually you can multiply both, right? And this can be separated also, and we just defined the coefficient of coupling is equal to K times of 51, and 521 is equal to K times of 52. Then these values if you replace it here, N1 K times of 51 by I1, N2 K times of 52 divided by I2. This can be treated as K square times of N1 51 by I1 into N2 52 by I2, right? So this is actually the M square value, or this can otherwise be treated as, so M square is equal to K square times of L1 into L2, or M is equal to K times of L1 L2 square root, or K is equal to M by square root of L1 L2. Got it? Is this understood? So this is how actually we will find out the coefficient of coupling. Any questions? Anybody else other than Ashish? Right? Okay, great. Now actually, so this mutual inductance will have actually the directional nature. Meaning, suppose if there are two different things, suppose actually if two persons are there, one person can support the other person, or actually one person can oppose the other person also, right? So two possibilities are there. So that is, so this mutual inductance right may be additive or oppositive. Or oppose the original flux, right? So it may be the additive, or actually it may be the opposite one. Suppose actually we have actually the same coil. Let us say we have one coil here and we have one coil here. Now the current actually is flowing in the same direction, both of these. Now in this case actually, let us say this is of N1 and this is of N2, and this is actually N1 phi1 by I1 and this is N2 phi2 by I2. Right, N1 phi1 by I1 and N2 phi2 by I2. This is the self-inductance. So this is L1 and this is L2. So N1 and N2 may be different, but the current may be same in this particular case. So the current may be the same magnitude of current, it can flow, or actually it may be the different current also, it can flow. But actually we have taken as the different, but ideally these two are same because these are the series circuit. Now the coupling may be in such a way that these two may be additive or these may be opposite also. Suppose if it is additive, then actually there is a mutual inductance. So some portion of the flux from here actually it will come and then actually it will increase the EMF that is going to be induced. Even the same case actually the flux is produced by this flux is additive to the second one and it will increase the EMF that is going to be produced. So effectively the amount of the EMF that is going to be produced because of the first coil, it's not just because of the single coil, it is even the because of the other coil actually which is influencing the first one. That means the effective inductance can even be treated as, so if you take this one, right? So this is, if you take this one, so this is L1 d phi by r, L1 di by dt, and here actually I1 is equal to I2 is equal to I. So I is equal to I1 is equal to I2. So L1 di by dt is the EMF induced in the first coil plus mutual inductance because of the second coil on the first one and because of the same current di by dt, and the EMF induced because of the second coil is L2 di by dt, and again the mutual inductance of the first coil on the second one is M into di by dt, and overall actually this is L1 plus L2 plus 2 times of M into di by dt is the overall LDI by dt if you wanted to replace with a single inductance like this. So if two inductances are jointed in series, then in that case the effective inductance will be L1 plus L2 plus 2M. Got it? Assuming that these two are additive in nature. Is this understood? Right? Okay, great. So now actually if these are opposite in nature, so if it is opposite in nature, then actually the original flux, if it produces phi, then actually because of M actually it will reduce some flux here. That means this sign will be opposite. And even the other one also it will be opposite because the first one opposes the second one, then the second one opposes the first one. So it is automatically actually it will be exactly the same kind of behavior actually these two will show, and hence actually this is plus or minus. If it is additive, it is plus. If it is opposite, then actually it is going to be minus. So for this actually usually graphically what we can show is, so there is a coil here and there is our coil here. So this is actually the series additive, and the same thing actually can even be represented this way, and this is actually right. So if these two wires are there and here this current is flowing in this direction, but the current actually is flowing in the opposite direction for the second coil. Now in this case actually this is plus 2M and this is actually minus 2M. This is how actually it will show. But actually making this diagram so complicated is not suggested. Rather than that, is there any better way of representing the same information? Right? Is there any better way of representing the same information? So that is, there is something called dot convention. This is very, very important to understand this dot convention, because all the problems actually you will make mistake just because of not understanding this dot convention perfectly. But hardly it will take actually 5 minutes for us to understand, just 5 minutes. But if you don't understand that, it will make the entire problem complicated for you, and for sure you will make mistakes. right? If you don't understand this dot convention. So what is this dot convention is, in case of series connection, actually, it will be easy to understand. So series connection, actually, if this is the one, right? And both are series connections only in both of these cases. If there is a dot here and there is a dot here, then the current is actually entering exactly at the same position. Then this is called as the additive nature. So this actually, the equal inductance will be L1 plus L2 plus 2M. Suppose if it is the opposite direction. So there is a dot over here, there is a dot over here. Now here, if the dots are placed at this particular point, so the exit point is the entry point for the second one. Now in this case, L1 plus L2 minus 2M. So this is the equivalent inductance in case actually if the dots are actually placed exactly at the same position. Now suppose actually if the dots are actually, this is one dot and this is one dot, actually if you put it, then actually this is also opposite. L1 plus L2 minus 2M. Got it? So this is how actually the dot convention is used in the case of the series inductances. Got it? Any questions on this dot convention? Dot convention is actually very, very simple. So wherever the current is entering, right? So in both the cases, actually, if it is entering exactly at the same point, this is an additive, right? So this is actually plus 2M, right? And opposite actually can be two different categories. Suppose actually this exit point is the entry point here. Then in this case, actually both are opposite in nature, right? Exit point and opposite point are matching. Now in this case, actually we call this as the opposite. So this dot will decide. And this in this case, actually L1 plus L2 minus 2M. And so entry point and exit point are one and the same. Now in this case also, these two are actually opposite in nature. So this is also minus 2M. Got it? Understood? And the dot can be placed the other way also. Suppose actually, and there is one dot here and there is one dot here. So should I keep it plus or minus? This is also plus, right? So plus 2M here and plus 2M here, minus 2M here and minus 2M here. So this actually you can easily understand without having much of difficulty. But the parallel connection actually it will make mistake. Now, so I will give you the parallel connections. You try to tell me what are the plus and what are the minus. Okay. Now tell me. Yeah. So which one is additive? Which one is opposite? So the first case actually you take it. So is this an additive or opposite? So both are actually the top dots, or actually maybe bottom, it doesn't matter. You can keep it actually both the dots here also. As long as the direction of the currents are same and the dots also located exactly at the same position, this is additive. Got it? So the direction of the current should be same and the dots also should be located exactly at the same position. Then actually it is additive. Now here, see this. Is this additive or opposite? What about this one? Any other answer? So this is negative, this is plus, and this is plus, this is negative. Let me explain. So here actually you can say actually in a single statement actually you can remember all these four diagrams. The single statement is, so either the direction or the dot are opposite, then that is negative. Either the direction or the dot. Now in this case, dots are opposite, but the direction of the current is same. Dot is top and bottom, right? So hence actually this is a negative. And here dots are same, but the direction is opposite. Got it? Direction is opposite. Now in this case actually this is also a negative. Now it has to be both the downward direction and the same dots are both opposite. So this is also opposite, this is also opposite. Got it or not? So with that single statement actually you can remember this, right? So otherwise actually it will make a lot of confusion. So now actually you might have confused, right? So this diagram actually made a mistake because actually, so these are actually different types of dots and direction actually. The current direction also does matters and the dot location also does matters a lot, right? So that's actually this kind of connection actually you have to assure properly. You just remember that statement, either the direction or the dot. If it is opposite, then that is negative. Otherwise it is positive. So if it is opposite, both has to be opposite. So top dot and bottom direction and the top direction. Both are opposite, positive. Both are same, positive. One opposite, one negative. So here actually one opposite, negative. Got it? Okay. So this is about the dot convention. And based on this actually you can solve anything. Now actually if you wanted to identify any series circuit or parallel circuit or anything like that, you can simply actually replace with the mutual inductance and then actually you can calculate anything whatever you want. So there is an equivalent circuit actually usually it was written. So that is if there are two, so let us take this particular scenario. Both are top dots and the currents are downwards. Right, so it is actually the additive nature because actually both are the same direction and the same dots. So this is actually the additive. Now in this case, here it can be replaced with, there is a single coil here and which is of L1, right? So L1 di1 by dt, and then actually you can keep a variable source here, and this is m into di2 by dt. And similarly, you can keep a coil here, and then actually this is the plus and minus. This is L2 di2 by dt and m di1 by dt. And this is the equivalent circuit for this particular dot convention. Got it? Right? For this particular dot convention, actually, you can keep it like this. Suppose if it is opposite, then actually these signs actually will be opposite. So that actually you can replace with this equivalent circuit with a variable voltage source, and then actually you can simplify the circuit, and whatever you want actually you can calculate it. Got it? I hope you understood this. So note down this problem. Find the total inductance of the three series connected coupled coils. As shown, right? And this is, so there are three different coils. So L1 is 1 Henry, L2 is 2 Henry, L3 is 5 Henry. So this is L1 is 1, L2 is 2, L3 is 5. And then, so this is one dot, this is one dot, this is one dot. Two, M23, M113. And these values are M12 is 0.5, M23 is 1 and M13 is 1. Now find the equivalent inductance of this entire circuit. Right? Can you calculate the equivalent inductance? $13 Henry. Any other answer? Naik, what about you? But none of the answers are correct. Nine. Okay. Okay. So let me explain. See this. We have got actually three different coils. Now actually I'll write the equivalent inductance value after removing the dot convention. Now if you notice, the first coil actually it is having an inductance of L1, but it is having the mutual inductance with the second coil and the third coil. And the second coil actually, it is actually, so this is actually dot is here and dot is here. So these two are actually additive in nature. Both are actually exactly at the same position. And the second coil also is having the mutual inductance with the first one and this coil, right? And dot is here and dot is here. So opposite dots are there. Now actually it is the subtractive in nature, right? I hope you understood that point. Yes or no? So this is additive, this is opposite. Now in this case, actually the effective inductance of the first coil will be its self-inductance and the mutual inductance of this. So M12, so M12 is 0.5 and this is actually opposite. So this is -1. No, additive is actually, I have given the dot convention, right? So additive means if the direction of the current is same, then actually the dots are located at the same entry points here, then additive. So here actually the dots are opposite, hence actually it is opposite. You got it? Right? So both are entry here. So that is the reason actually the dots are exactly at entered position, hence actually it is additive. So this is actually 1 and 0.5 is additive and 1 is opposite. And the second coil you take it, so this is actually the self-inductance is 2 and because of the first coil actually it is additive. So hence actually this is the 0.5 is added and because of the second coil this is also opposite dots, hence actually this is going to be opposite in nature. This is the second coil. Coming to the third coil, and it is having a self inductance of 5, and so this is also opposite and this is also opposite, both are actually opposite. And third coil actually M13 is opposite negative, so -1, and so M23, so M23 also is opposite and this is also negative, right? So effectively the first coil is 1 minus 1 will cancel, so this is going to be 0.5, and the second coil is 2 minus 1, so this is going to be 1.5, and this is 5 minus 1, this is going to be 3. So total actually 5 Henry. Got it? So that's why actually I am telling you, you people make mistake because of this dot convention, right? But once you know the dot convention, it is very easy, straightforward. There is no confusion in this, very simple concept. The current is entering everywhere. Now at the entry point, if dot is there for both the coils, then that is additive. One dot at entry point, one dot at exiting point, then that is opposite. So here in both of these coils actually it is additive. And this coil, so entry here and exit point. So these two are opposite. And this is also entry here and opposite, the second coil. These two are opposite, right? First and last is opposite, second and last is opposite, and first and second are additive. Understood, Naik? Right? So any other questions? So based on this actually you can solve anything, and I'll give you one problem and you try to solve with the help of all the concepts involved in this. You do this. Find the drop across RL. Use the calculator. Across RL. And this kind of questions actually you can expect in the exam also. Ten at an angle of 0. Ten at an angle of 0. J2, J1. So this is J2 and this is J1 minus J3 K equal to 0.5. The dots are located at this point and this point, and there is a coefficient of coupling K is equal to 0.5. Yeah, that's it. Right? So here actually the K value is given, right? It's not the mutual inductance that was given. Now here, so this is actually omega L1 and this is omega L2. So J times of omega L1, J times of omega L2. And J times of omega M actually you can calculate with the help of the coefficient of coupling. So this is actually, if you take the simple calculation, so omega M, right? And this value is K times of square root of omega L1 into omega L2, right? Or else actually omega can even be replaced with K times of omega into square root of L1, L2, and this is M times. So omega you can cancel, M is equal to K times of L1, L2 under root. Got it? So this way actually the coefficient of coupling actually will help you in identifying the mutual inductance. Or else actually if you directly wanted to calculate the reactance itself, then in that case actually you can take this particular scenario. So this is actually 2, this is going to be 1. So coefficient of coupling is, so this m is equal to, straight away you can take it. So 0.5 into square root of 1 into 2. So this is root 2 by 2 which is equal to 0.707. And this is the mutual inductance straight away, 0.707. Got it? Understood? Now you can solve this particular circuit. There is two different inductances are there and one capacitance is there, one load resistance is there. The problem is find the drop across this particular resistance. So this inductance was given, this inductance was given, this reactance was given, and this is 10 at an angle of 0. And the mutual inductance is the key point which we have calculated just now as 0.707. Got it? Is this additive or opposite? See, it may not be the same current actually that is going to be flowing, but as long as this is entering here and this is entering here, because this is the only source. The current is in this direction, the current is in this direction, opposite nature, right? So this way actually you can use this concept and try to calculate the amount of the voltage drop in the load resistance. This is an assignment for you. Got it? And with this actually I am done with this coupled circuits and we have only one last topic, that is the graph theory. Got it?